This doesn't make any sense.
Not everything does. Not everything has to. Great distances in an instant. Yes. Through time. Looking for you.
Imagine, the world we live in is just one of countless universes. In Doctor Strange, we see the multiverse, parallel worlds where other versions of us live with different destinies. But here's the question, is it just Marvel fiction? Or, do scientists actually believe the multiverse could be real? Today, we'll open the doors of imagination and science. From the wildest physics theories, to the latest research that makes scientists wonder, are we truly alone in this universe, or just one of billions of other realities? The multiverse isn't just a comic book idea. Pop culture has been playing with this concept for decades, and in recent years, it's exploded in popularity. In Doctor Strange in the Multiverse of Madness, reality shatters. Strange meets his variants in other universes, and even encounters the Illuminati ruling under completely different laws. In Loki, the multiverse is shown as infinite branches of timelines. One small decision can create an entirely new path of reality. Everything Everywhere All at Once takes the multiverse to a chaotic, absurd level. Our alternate selves could be anything, a chef with a raccoon on their head, or even a talking rock. And of course, Spider-Man, No Way Home brought together 3 Spider-Men from different universes. That scene made millions wonder, if the multiverse is real, could there be another version of me out there? It all sounds wild, but here's the catch. These movies aren't just making things up. They borrow from real physics theories, from quantum experiments, from debates among scientists. The big question we need to answer is, among all these cinematic visions of the multiverse, which one is closest to real science? Which ones are pure fiction, and which might actually be possible? Now we dive into the scientific heart of the multiverse idea. Not just Marvel's fantasy, not just Doctor Strange, but real physics. For decades, scientists have debated whether our universe is unique, or just one among countless others. In this segment, we'll break down 4 major foundations: the many worlds of quantum mechanics, cosmic inflation and bubble universes, the string theory landscape, and Max Tegmark's levels of the multiverse. Let's explore them, one by one. Our first stop is the quantum world. In 1957, Hugh Everett proposed something radical. The wave function never collapses. Every possible outcome of a quantum event actually happens, but in different, branching realities. Think of a river splitting into countless streams. We ride one branch, but all the others exist too, carrying different versions of events, and perhaps different versions of us. The key mechanism here is decoherence. When a quantum system interacts with its environment, the branches stop interfering with one another. They evolve independently, as if they were separate universes. This concept, refined by Wojciech Zurek and others, is well studied. What about experiments? Quantum superposition has been observed not just in photons or electrons, but in large molecules, buckyballs with 60 atoms, even organic molecules of thousands of atoms. The bigger the system, the faster decoherence kicks in. But the bottom line, quantum mechanics holds. Does this prove many worlds? No. The experiments support quantum theory, but interpretations differ. Many worlds is elegant, consistent, but still untestable directly. Punchline: this is not movie magic. It's a serious interpretation of the same equations that power quantum computers. Next, cosmology, cosmic inflation. Alan Guth and Andre Linde in the early 1980s proposed that, after the Big Bang, the universe expanded faster than the speed of light, stretching trillions of times in a fraction of a second. This solved puzzles about why the cosmos looks so uniform and flat. But here's the twist. In some models, inflation doesn't end everywhere at once. Instead, it keeps going in some regions, forming bubble universes. Our bubble is one of them. Countless others may exist, each with different physical laws. Can we test this? If another bubble ever collided with ours, it could leave scars in the cosmic microwave background, faint circular patterns in the oldest light of the universe. Teams have searched WMAP and Planck satellite data for these signatures. So far, nothing conclusive. The Planck mission confirms inflation works. The spectrum of fluctuations matches predictions perfectly. But evidence of collisions, of other bubbles? Still missing. The takeaway: inflation is strongly supported. Multiverse through eternal inflation remains possible, but unproven. Third, the world of string theory. In this framework, all particles and forces are vibrations of tiny strings. The challenge: string theory has too many solutions. How the extra dimensions curl up determines the physics we see. There may be an astronomical number of possible configurations. Estimates often cite about 10 to the power of 500. Leonard Susskind called this the string landscape. Imagine a cosmic catalog of universes. In one, gravity is stronger. In another, electrons are lighter. In many, stars never even form. If that's true, then multiverse isn't optional, it's inevitable. We simply inhabit one of the few universes where life is possible. This is the anthropic argument. The problem: testability. If 10 to the power of 500 possibilities exist, how do we make unique predictions? Critics argue this pushes physics to the edge of philosophy. But still, the string landscape is a serious reason why many physicists take the multiverse seriously, even if they're uncomfortable with it. Finally, Max Tegmark organized all these ideas into 4 levels of the multiverse. Level 1, regions beyond our cosmic horizon, possibly with copies of our world. Level 2, bubble universes from eternal inflation, with different constants. Level 3, the quantum many-worlds, branching realities. Level 4, every mathematical structure exists as a reality. This map helps us separate what is testable from what is philosophical. Level 1 and 2 are connected to cosmological data. Level 3 is consistent with quantum experiments, though not uniquely provable. Level 4 is almost pure metaphysics. The punchline here: multiverse is not a single theory. It's a spectrum of ideas, ranging from solid science to radical philosophy. So here's the bottom line of this segment. Multiverse is not one idea. It's many. Some parts, like inflation, are backed by data. Others, like many worlds, are clean interpretations of quantum mechanics. Still others, like the string landscape or level 4 multiverse, are bold speculation. What makes this fascinating is that we're not just talking about science fiction. These are real, ongoing debates among the world's top physicists. In the next segment, we'll look at the evidence hunt, from the cosmic microwave background, to gravitational waves, to the most cutting-edge quantum experiments, and ask, are we getting closer to proving the multiverse, or are we staring at the limits of science itself? In the previous segment, we explored the theories, from many worlds to cosmic inflation and string theory. Now comes the crucial question: what evidence do we actually have? This is where things get exciting, because physicists are not just writing equations, they are searching for signatures in the sky, in the lab, and even inside quantum experiments. In this segment, we'll break down the evidence hunt into 4 arenas. 1. The cosmic microwave background, our baby picture of the universe. 2. Gravitational waves, ripples in spacetime. 3. Large-scale structure and astrophysical observations. 4. Laboratory quantum experiments that test the foundations of reality. Let's dive in. The cosmic microwave background is the oldest light in the universe, radiation left over from the Big Bang, stretched into microwaves over 13.8 billion years. If other universes ever collided with ours, the crash might have left scars in this ancient light. Researchers like Stephen Feeney and colleagues developed algorithms to search WMAP and later Planck data for circular patterns, concentric rings in the sky that could be the fingerprints of bubble collisions. The result: Planck data revealed some anomalies, but nothing conclusive. No clear evidence of another bubble universe. However, Planck did give us powerful support for inflation itself. The tiny quantum fluctuations during inflation seeded the large-scale structure of the cosmos. The spectral index of these fluctuations, around 0.965, matches predictions beautifully. So the CMB gives us a paradox. It confirms inflation, the mechanism that suggests a multiverse, but it has not revealed the smoking gun of other universes. Punchline: the CMB is a treasure map. It shows us where to look, but so far, no X marks the spot. Next, gravitational waves, ripples in spacetime predicted by Einstein and first directly detected in 2015 by LIGO. These waves carry information from some of the most extreme events in the universe: black hole mergers, neutron-star collisions, and potentially, even the earliest moments after the Big Bang. Here's the multiverse connection. Inflation should produce a background of primordial gravitational waves. If detected, they would not only strengthen the case for inflation, but also give indirect support to models of eternal inflation and bubble universes. In 2014, the BICEP-2 experiment in Antarctica announced it had detected a pattern of B-mode polarization in the CMB, thought to be the signature of primordial gravitational waves. The scientific world exploded with excitement. Some even said, we may have proof of inflation, and by extension, the multiverse. But later analysis with Planck data showed the signal was mostly dust in our galaxy, not primordial waves. The excitement faded, but the search continues. Today, upgraded detectors like BICEP/Keck and the upcoming Lightbird mission aim to push sensitivity to new limits. If they find primordial gravitational waves, it won't be direct proof of other universes, but it will make the inflationary multiverse scenario much harder to ignore. Our third arena, the structure of the cosmos itself. If our universe is just one bubble in a larger multiverse, could we see hints in how matter is distributed across billions of light years? Some studies have searched for cold spots in the CMB, regions with unusually low temperature. One famous cold spot in the southern hemisphere sky has sparked speculation. Could it be evidence of a collision with another universe? Most cosmologists argue the cold spot can be explained statistically, or by large voids in the distribution of galaxies. But the possibility remains intriguing. Other researchers examined the alignment of cosmic structures, like the so-called axis of evil in the CMB, a strange alignment of temperature fluctuations. Some see it as a clue of something bigger, others think it's a statistical fluke. So far, the large-scale structure gives us tantalizing anomalies, but no consensus. Still, the universe may be whispering to us in patterns too subtle for current instruments to decode. Now let's return to the quantum lab. If many worlds is real, every quantum event branches reality. But how could we ever test that? While direct proof may be impossible, experiments continue to push the boundary of quantum mechanics. We've seen interference not just in electrons and photons, but in molecules containing thousands of atoms. We've observed decoherence in action, how entanglement with the environment hides quantum superpositions, making them appear classical. Some researchers even suggest experiments with quantum computers could someday distinguish interpretations of quantum mechanics. For example, if many worlds is true, entanglement may be understood as computation across parallel branches of reality. Right now, no experiment singles out many worlds as uniquely correct. But the fact that quantum mechanics has never failed, even at larger and larger scales, keeps the door wide open. Punchline: the lab shows us that quantum weirdness is not going away. If anything, it's getting bolder. Beyond these main arenas, there are other speculative clues. Some theorists explore the idea that dark energy, the mysterious force accelerating cosmic expansion, might be linked to a multiverse landscape of possible vacuum states. Others suggest black holes could act as gateways, where new universes are born inside. These ideas remain highly speculative, but they keep the conversation alive. And then there's the anthropic principle, the observation that the laws of our universe seem finely tuned for life. Multiverse models, especially from string theory, provide a natural explanation. We live here because here is one of the rare universes where life can exist. It's controversial, but it's part of the evidence landscape. So where does this leave us? We've seen that the evidence is mixed. 1. The cosmic microwave background confirms inflation, but no bubble scars yet. 2. Gravitational wave searches are ongoing, with promises of breakthroughs ahead. 3. Large-scale structures show anomalies, but nothing decisive. 4. Quantum experiments prove the weirdness of physics, but don't single out many worlds. And 5. Speculative ideas remind us, the multiverse is as much philosophy as it is physics. The truth is, the multiverse remains unproven. But it is not unscientific. It is a frontier where data, theory, and imagination collide. For scientists, the multiverse is not about believing in Marvel fantasies. It's about following the math, the evidence, and the possibility that reality is far bigger than we ever imagined. In the next segment, we'll tackle the big picture. If the multiverse is real, what does it mean for humanity, for science, and for our place in the cosmos? We've explored the theories. We've examined the evidence. Now comes the deeper question. If the multiverse is real, what does it mean for us? Are we just one tiny version of ourselves, among infinite possibilities? Is our civilization only one fragile spark, surrounded by countless others we may never meet? And if so, what does life, choice, and the future of humanity really mean? Imagine that in another universe, there's a version of you who made a different choice. Maybe in that universe, you live in a different city, chose a different career, married someone else, or maybe you never existed at all. This idea can feel thrilling, or terrifying. On one hand, the multiverse might make us feel small, as if our life is just one scenario among countless others. But on the other hand, it makes our version of life even more precious. Every choice we make is unique to this path. We live in this branch of reality, and this branch can only be lived once. From a cosmic perspective, the multiverse teaches humility. If our universe is just one bubble, then human achievements, from the pyramids to the internet, are just dust on a cosmic scale. But that doesn't make them meaningless. In fact, it can inspire us to dream bigger. If reality itself is wider than we imagined, why shouldn't our civilization aim higher too? Space technology, renewable energy, artificial intelligence. Maybe these are only the first steps. Perhaps one day, humanity will find ways to push beyond our bubble, or at least understand our true place within a much greater reality. The multiverse also touches a sensitive frontier, the relationship between science, religion, and philosophy. For some, the multiverse offers a scientific answer to an ancient question. Why do the laws of physics in our universe seem perfectly tuned for life? In a multiverse, the answer is simple. We exist here because only here could life exist. For others, the multiverse deepens spirituality and awe. If creation is this vast and complex, then surely a greater mystery lies beyond it. What's clear is that the multiverse forces us to expand our thinking, beyond tradition, beyond one definition of reality. Then comes the existential question. If there are other versions of us, does that make this life less meaningful? Some philosophers argue that the multiverse could diminish the significance of our choices. But another perspective says, every version is real within its own branch. None is more important or less real than another. That means our life, right here, still matters. In fact, the multiverse shows us that meaning doesn't come from cosmic uniqueness, but from personal experience. Love, suffering, laughter, struggle, they are real only here, in our branch. And that is enough. Of course, the multiverse has taken over pop culture. Marvel, DC, sci-fi films, anime, they all use it as a stage for storytelling. But pop culture isn't just entertainment. It trains our imagination. It makes science feel closer. It makes people ask, what if this is real? Scientists like Albert Einstein, Carl Sagan, and Stephen Hawking all emphasized imagination as essential. Without imagination, there would be no theory of relativity, no space exploration. And without pop culture, maybe a whole generation wouldn't even care about the mysteries of the cosmos. The multiverse is the perfect example, the meeting point of fiction and physics, story and science. In the end, the multiverse may be real, or it may be a mathematical mirage. But either way, the idea has already changed how we see the world. It reminds us that reality is larger than our understanding. It shows that science is not just about numbers, but about meaning. And it challenges us to keep asking, who are we, and what is our place in the cosmos? If the multiverse is real, then out there, infinite versions of us may exist. But the one watching this video right now, this version of you, is the only one that matters to you. And maybe, that's enough to make us feel both humbled and awestruck by the grandeur of the universe. Every great scientific idea eventually faces a trial, and the multiverse is no exception. For some scientists, it's the most elegant explanation for the mysteries of the cosmos. For others, it's nothing more than science fiction disguised as theory. Tonight, let's step into the arena of ideas, where the greatest minds clash over one question: is the multiverse real, or just a fantasy? On one side, we have the supporters. Physicist Andre Linde, one of the fathers of cosmic inflation, argues that the multiverse is a natural outcome of inflationary theory. If inflation created multiple bubbles of spacetime, then each bubble could have its own laws of physics. In his words, the multiverse is not a theory. It's a prediction. Then there's Max Tegmark from MIT, who divides the multiverse into 4 levels. For him, it's not just about physics, it's about mathematics itself being reality. He says, if math is real, then so are all its solutions, including universes where the laws of physics are completely different. And don't forget Stephen Hawking. In his later years, Hawking suggested that the multiverse could explain why our universe seems fine-tuned for life. We exist in this universe because it allows life, and countless others do not. For the supporters, the multiverse is not wild speculation. It's the best explanation for why the cosmos looks the way it does. But across the arena, the skeptics stand firm. Physicist Sabine Hossenfelder argues that the multiverse isn't science at all, because it can't be tested. If other universes are forever beyond our reach, then how can we ever prove they exist? She calls it a dangerous move away from science into philosophy. George Ellis, a renowned cosmologist, agrees. For him, the multiverse may sound appealing, but it risks turning physics into storytelling. If every outcome exists somewhere, then any theory can be justified. And if everything is possible, then nothing is falsifiable. The skeptic's verdict is sharp. The multiverse might be beautiful. It might be fun for movies and books. But without evidence, it doesn't belong in science. Yet, between the clash of extremes, some scientists stand in the middle ground. They admit, the multiverse is not directly testable now. But they also argue, neither was black holes, once. Neither was quantum entanglement. History shows us, sometimes, bold ideas wait decades before evidence catches up. So perhaps the multiverse is not today's science, but tomorrow's. In the end, the debate remains unresolved. The multiverse is a battlefield of ideas, half science, half philosophy, half imagination. Maybe it's real, waiting to be discovered. Maybe it's fantasy, destined to remain in stories. Or maybe, the truth lies in a place we haven't even imagined yet. And that's what makes the multiverse one of the greatest debates of our time. Doctor Strange opened the door to the multiverse with magic. Marvel showed us parallel worlds with dazzling visual effects. But in reality, science is trying to open that same door in a very different way. Not with spells, but with mathematical equations. Not with a magic ring, but with cosmic telescopes and quantum experiments. Movies make us wonder. Science makes us ask, what if all of this is real? Every time we watch the multiverse on screen, we're really seeing a mirror of human imagination. Cinema gives us fantasy, but behind it, there's always a spark of real science. Once, traveling to the moon was only science fiction, until Neil Armstrong left his footprint there. Today, the multiverse feels impossible. But tomorrow, we may find evidence. Fiction fuels imagination. Science provides direction. And together, they lead us into territories we never thought possible. So the question remains, do we truly live in a multiverse? Or is it all just a quantum illusion, making us believe other worlds exist? Until the evidence appears, we remain explorers, wandering in this one universe. And maybe that's the real wonder, that even this single universe is more mysterious than we can ever understand. The multiverse may exist, or it may not, but one thing is certain: our curiosity is the strongest door we've ever opened into the mysteries of the cosmos.